Okay, so in quantum statistics, we have two, right? One is Fermi-Dirac statistics, and the other one is Bose-Einstein statistics. Fermi-Dirac statistics is applicable for fermion type particles. Okay, fermion particles. Bose-Einstein statistics are applicable for bosons, boson particles, right? What are fermions? Fermions are particles having half integer spin. Okay, particle having half integer spin is what we call as particles having half integer spin. Half integer spin means, okay, if spin of the particle is 1/2, 3/2, 5/2, etc., those particles are called fermions. So fermions are particles having half integer spin. Okay, for example, electrons, right? Proton, neutron, most of the subatomic particles, okay, comes under fermions, right? Then what are bosons? Bosons are particles having integer spin. Bosons are particle having integer spin. Integer spin means 0, 1, 2, 3, 4, etc. If the spin of the particle is 0, 1, 2, 3, 4, we call those particles as bosons. Okay, so in boson we have photon. Photon is a quantum particle whose spin is 0. Okay, photon, phonon, Cooper pair of electrons. Cooper pair of electrons. Right, these are all few examples. We have many examples. Here I have given only few. Okay, these are all few examples for boson particles. So quantum statistics is applicable for particles having spin. Okay, then we can apply quantum statistics. Quantum statistics is applicable only for particles having spin, right? Whereas for Maxwell-Boltzmann statistics, you need not worry about spin of the particle. Spin is not important. Okay, so remember these two are the two different quantum statistics we have. Fermi-Dirac statistics. Then the other one is Bose-Einstein statistics, right? Fermi-Dirac, the particles which are used are the particles which are which obey Fermi-Dirac statistics are called fermions, and particles which obey Bose-Einstein statistics are called bosons. Fermions have half integer spin, whereas boson particles have integer spin. Okay, now let me start the first one called Fermi-Dirac statistics. Fermi-Dirac statistics. As I told you, this statistics is applicable for particles having half integer spin. Okay, so what are the essential postulates here? Fermi-Dirac statistics is in particles must be identical. Okay, and particles must be independent. Okay, particle must be identical particles, and the particle must be independent. Independent means there should not be any attraction or repulsion exist between particle. Okay, like say for example ideal gas, right? So particle should be identical, independent, right? Then next one, and particles must have half integer spin. Spin should be of 3/2, 5/2, etc. And these particles are called fermions. Okay, then since particles having spin must obey Pauli principle. Okay, so this statistics obey Pauli principle. It obey Pauli principle. Yeah, this statistics obey Pauli principle, and according to Pauli principle, the wave function, total wave function, right, must be anti-symmetric. Total wave function, okay, total wave function must be anti-symmetric with respect to exchange of any two particles. Okay, here particles are fermions. Okay, here particles are fermions, right? For fermions, so if you have a collection of identical fermions, right? Then if you exchange any two identical fermion, then the total wave function, okay, should change the sign. Sign of the wave function should change. If sign changes, we call that wave function as anti-symmetric wave function. So keep all this information. For Fermi-Dirac statistics, particles must be identical and independent. Okay, then particle must have half integer spin. If particles have half integer spin, those particles are called fermions. Then third one, since the particles have spin, they must obey Pauli principle. For fermions, total wave function must be anti-symmetric. For fermions, total wave function must be anti-symmetric. Okay, then next important point, for fermions, this is very, very important. Then in each state, we can place only one particle. Only one particle. I repeat once again, here particle means fermion. Okay, only one particle can be placed in an energy level or state, in an energy state. Okay, so these are all some important conditions, right? And this is very, very important. Keep this in mind. You cannot place more than one particle in an energy state. Okay, then the next one. Yeah. Let the total number of particles, okay, in a system, right? Or I'll give like this. Consider a system. Now, consider a system, okay, containing total number of particles n. Capital N represent total number of fermions present in the system. Let the total volume be V, okay, and let the total energy be capital E. So total N, total V, that is total volume and total energy. I'm going to keep all these things as constant. Okay, total number of particles should not change. Okay, so total number of particles is a fixed quantity. Similarly, total volume of the system also fixed one, and total energy also fixed. Okay, so we can say that the system is a canonical ensemble. Okay, I told you already that I told you if N, V, E kept constant, then the system can be called as a canonical ensemble. Right now, what is the thermodynamic probability formula for Fermi-Dirac statistics? Okay, say for example, I have assume that I have 5 states, okay, and two particles. Okay, and I forgot to give this information. I'm sorry. I told you the particle should be identical in size, then they should be independent, and the most important one, the particles should be indistinguishable particles. I forgot to give this information, note down. Indistinguishable particles. Particles must be indistinguishable. All are same particles. Okay, you cannot distinguish one particle from the other one, right? So if see, I cannot say that this particle is A and this particle is B. Okay, we cannot say like that because the particles are indistinguishable now. Now listen, so how many states are there? There are 5 states and we have only 2 particles. I have told you already, in each state we can place only one particle. Okay, so this is one particular energy level. This level has 5 degenerate states and this level has only 2 particles. And I told you in each state we can place only one particle. Okay, so now how many possible ways that you can arrange the 2 particles in these 5 states? Can anyone give the answer? In how many ways you can place this particle? Or I'll do one thing. Instead of 5, I'll make it into 3 so that our task will be simple. Yes. Anyone? We have 3 states and 2 particles. You can place one particle in one state, that's all. Using this idea, how many ways that we can arrange?
3, sir.
Okay, yes. So this is one way. This is one way. This is another way, right? And this is another way. Is there any other way apart from this? Anyone? Is there any way of arranging the 2 particle apart from this? No. Correct, only 3 ways. Okay, so if the number of states are fixed and number of particles are fixed, you can find out how many ways that the particles can be arranged in those allowed states. Okay, for this we can also use the formula W is equal to GI factorial by Ni factorial into GI minus Ni factorial. Okay, see, by intuition also you can find this, and you can also find by formula method. Okay, see here how I'll use formula. See, we have totally 3 states. So G represent number of states. So how many states are there? There are 3 states. So 3 factorial divided by how many particles are there? Ni represent number of particles. So we have 2 particles, so 2 factorial into G is 3, N is 2. So 3 minus 2 is 1 factorial. Okay, what's the value of this? 3 factorial is 3 into 2 into 1. 2 factorial is 2 into 1. 1 factorial is 1. So if we cancel, you will get the answer as 3. Okay. So for Fermi Dirac statistics, you can use this formula to calculate thermodynamic probability. Okay. Now, what I'm going to do, see this. One second. Let me save this one. And, one second. Yeah, I'll save the image and. Okay. Yeah. Now, listen. Suppose I have a number of energy levels. Okay, number of energy levels. This level as energy E0, this level as energy E1, this level as energy E2. Like this, we have so many levels. Okay, so many levels, and I have another energy level EI. EI. Okay, we have many levels like this. Okay, now listen. In each level, so this is energy. In each level, there are a number of states. Okay, this is state 1, state 2, state 3, state 4. Like this, I have so many states. Assume that there are G0 states. Okay, in the ground level. In the ground energy level, we have G0 states. And in the first excited level, similarly, I have many states in the first excited level. Say, for example, I have G1 states in the first excited level. Similarly, G2 states in the second excited level. Like this, I have many levels with many degenerate states. And the ith level, ith energy level also has some number of states, let it be Gi. Okay. Now, let us assume N0 particles present in the ground level and N1 particle present in the first excited level, N2 particle present in the second excited level, similarly Ni particle present in the ith level. Now, if you have G0 particles, sorry, G0 states and N0 particle, keep this in mind, G0 and N0. Listen, G0 can be greater than or equal to N0. Keep this in mind in all the levels. Okay, G value may be greater or equal to N0. N0 never exceed, or I can say Ni never exceed Gi. This is not allowed in Fermi Dirac distribution. Are you getting this point? Why? Because
Yes.
in each state we can place only one particle. Suppose if I have 50 states, okay, how many maximum number of particles can be placed here?
49.
No. What I'm asking, we have 50 states. In each state, we can place only one particle. If it is so, how many maximum number of particles can be placed?
50 particles, sir.
50 particles, that's right. So G0, N0 may be equal, or G0 may be equal. What is meant by that? You can place maximum 50 particle. You can place 48 also, 49, 47, 45. Okay, so at no point n particle, number of particle cannot exceed number of states. Is it correct? Can you understand this now? Can I place 51
Yes, sir.
particle here? Can I place 51 particle here?
Not possible, sir.
Not possible.
No.
That's all. That's what I'm saying. Okay, so this is not possible, right? Yeah. So in each level, okay, the number of particles Ni, right, should be equal to Gi or should be less than Gi. Okay, only these are allowed. Okay, now what is the thermodynamic probability for arranging N0 particles in G0 states? I have given the formula. So thermodynamic probability for the ground level is equal to G0 factorial by N0 factorial into G0 minus N0 factorial. Is it correct? This will give you number of ways of arranging N0 particles in G0 states. Excuse me, are you able to follow this? Any doubt?
Yes.
Similarly, for the first excited level, how many ways you can arrange N1 particle in G1 states? Okay, I'm sorry, G1 factorial, this is G1. Yeah, G1 factorial divided by N1 factorial into G1 minus N1 factorial. Like this, in each energy level, okay, we have many ways of arrangement. For ith level, okay, Wi can be written as Gi factorial by Ni factorial into Gi minus Ni factorial. Okay, listen. In each level, we can arrange many ways. Okay, the particles in the given states. Like that, we have so many levels. Now, what is the total arrangement? Okay, how to get that value? Listen, total arrangement, total, W total. Right? I'm going to call this as omega. Omega also gives you thermodynamic probability, but in this omega, I'm using this here because I'm talking about total thermodynamic probability. Because in each level, we have thermodynamic probability. Okay, now I'm going to find out the total. So what is total? Total means you have to multiply. You should not add, you should multiply. So W0 ground level thermodynamic probability, first level thermodynamic probability, exit level, then W2, etc., etc. If you multiply all these probability, okay, you will get the total. So the total thermodynamic probability omega is equal to, listen, since we are multiplying, you can put the general symbol pi. You know, real pi means multiplication. Pi of gi factorial by ni factorial into gi minus ni factorial. Okay, this is the formula we use to calculate thermodynamic probability. Okay, in the case of Fermi
Okay.
Dirac statistics. Right? Is there any doubt here? Anyone?
No, sir.
Yeah. So remember, this is the formula we use to calculate thermodynamic probability for the Fermi Dirac statistics. Now what we have to do, we should find out an expression for the most probable macro state. Yes, how to get that? One second. Yeah. So the total thermodynamic probability is equal to product of gi factorial divided by ni factorial into gi minus ni factorial. Here I value starts from 0 and it goes to number of levels that is available. Okay. If you put I equal to 0, it means ground state, ground level. If you put I equal to 1, first exited level. I equal to 2 means second exit level, like that. Okay, now what we have to do? We have to find out the most probable macro state. Okay, so how to get that? For this, you know the method I have told you in the last class also. Okay, you know the method. So we have to take logarithm of this, ln of omega. First we should take logarithm of this, then differentiate this dou ln omega by dou ni, and then put the value equal to 0. Put the value equal to 0. So you will get the most probable macro state. But here we have two constraints. What are the constraints? Total number of particles is constant and total energy also constant. By keeping these two, okay, constraint, you have to maximize the function. For this, we use the Lagrange undetermined multiplier method, and you have to derive that. I'm not going to derive. Okay, I'm going to give you only the final expression. So the final expression for Fermi Dirac statistics is this: ni by gi. Observe this carefully. Ni by gi equal to 1 over 1 plus e power alpha plus beta into ei. Okay, this is the expression for Fermi Dirac statistics, where alpha and beta are Lagrange undetermined multipliers. Lagrange undetermined multipliers. Okay, so remember, this is very, very important. Okay, any doubts, sir, up to this?
No, sir.
Remember what this formula will give you? This formula will give you number of particles in the ith level in the most probable macro state. Sir, keep this information in mind. So, you know very well, by varying the particle, you can get many thermodynamic probabilities. But what is most probable macro state? Most probable macro state is the macro state having highest value of thermodynamic probability. Okay, so in the most probable macro state, how many particles present in the ith level? Right? Number of particles present in ith level, right? How to get that value? Okay, so for this, we can use this formula, Ni by Gi equal to 1 by 1 plus e power alpha plus beta into Ei. Okay, now, this is the general formula for Fermi-Dirac statistics. Okay, next one. Now, what I'm going to do is, one of the important application of Fermi-Dirac statistics, Fermi-Dirac statistics is electron gas in metal. Electron gas in metal. In metal. It's a very important application of Fermi-Dirac statistics. See, in metals, you know very well, in metals, we have free electrons. Have you heard about free electrons? See, in atom, we have nucleus. Okay, atom has, okay, nucleus, and atom has the surrounding electrons. The electrons are attracted by the nucleus. Okay. In atom, the electrons are not free. Sir, observe carefully. In atom, electrons are not free. Suppose if I have an atom, so many electrons will be there, and all the electrons are attracted by the nucleus. This is one atom. Now, if I bring many atoms closer and closer and closer, so here each circle represent an atom. What will happen? The valence electrons present in the atom, okay, they'll come out. They'll come out. Okay, so what will happen? You'll get free electrons, right? The valence electrons of each atom will come out. Okay, suppose if we take silver metal, see if you take silver metal, in silver metal, each silver atom has one electron in the valence shell and they release that electron. Okay, they release that electron. Suppose this is the crystal lattice, right? After releasing electron, the silver atom become positive ions. It will become positive. Okay, and the released electrons, okay, they move throughout the crystal lattice freely. That's why those electrons are called free electrons. Okay, and silver atom also has bound electrons. Listen, the inner shell electrons, they never come out. Only the valence shell electron can come out, okay, and can move throughout the crystal, right? So the inner shell electrons are called bound electrons. One second. The inner shell electrons are called bound electrons, and the valence shell electrons that comes out are called free electrons. Okay, these free electrons, right? Each electron has a spin value of half. You know very well. So electrons are fermions, right? So in metals, we have free electrons. These free electrons moving throughout the crystal like a gas. Okay, that's why it is called electron gas. In this electron gas, each electron has a spin value of 1 by 2. I have told you in the beginning, if spin value is 1 by 2, we call the particle as fermions. Okay, so we have a large collection of fermions in a given piece of metal, right? So here, let the total number of electrons be n, and since the metal piece has some definite volume, so this volume is a constant, and let the total energy of all the electrons is equal to E. Okay, so by fixing all these three, okay, you can write the Fermi-Dirac statistics, Ni. Why I am using Fermi-Dirac statistics? Anyone?
To find the free
Obstacle.
electrons.
because here the particles are electrons. Electrons are fermions. So we have to use Fermi-Dirac statistics. So what is the formula? Ni by Gi equal to 1 by e power r. You can write in this way also, but I'll write the method I have given already. 1 plus e power alpha plus beta into Ei. This is the general formula. Now, in the case of metals, okay, in the case of metal, this alpha will be equal to minus Fermi energy. I'll write EF, Fermi energy by kBT. Sir, observe this carefully. In the case of metals, right? In metal, alpha is equal to minus Fermi energy by kBT. And beta, this is, we know very well. Beta value is always 1 by kBT. This we know. So by substituting these, okay, you will get an expression like this. I'll write the expression in the next page. Yeah, we'll get an expression that Ni by Gi equal to 1 over 1 plus e power e power EF Fermi energy minus Ei. I have taken kBT as constant. Okay. Yeah. So this is the expression for electron gas in metals. Okay. What is the Fermi energy? What is Fermi energy? Listen, at 0 Kelvin, listen. So we have so many levels. We have so many energy levels. And let us assume I have some number of particles, and the particles will occupy all these states, and assume that this is the level, highest level, the particles are occupied at 0 Kelvin. Okay, this level is called the Fermi level. So what is Fermi level? Fermi level is the highest occupied level. Fermi level is the highest occupied level at 0 Kelvin. Okay, 1 second, sir. Let me come back 1 second. Okay. Right, sir. Shall we continue? So what
Sir.
is, yes, sir. What is Fermi level? Fermi level is the highest occupied level. After that, all the levels are empty. See, after that, all the levels are empty. So it is the highest occupied level at 0 Kelvin. This is very, very important. Okay. So what is Fermi level? Fermi level is the energy level which is highest occupied at 0 Kelvin. Right? Sir, any doubt here? Any doubt?
Yes.
Okay. Now listen. At 0 Kelvin, if I plot this Ni by Gi, right, versus Ei, energy. I'm plotting Ni by Gi versus, see, I'm plotting this Ni by Gi versus the energy of the ith level. Listen, this is ground level. Okay, ground level at 0 Kelvin, ground level is fully occupied. Okay, so here Ni and Gi are equal, or I can say N0 and G0 are equal. If N0 and G0 are equal, then thermodynamic probability of the ground level should be 1. Similarly, this level should be 1. So up to Fermi level, okay, up to Fermi level, all the levels have thermodynamic probability as 1. Okay, so yeah, see Ni value and Gi value, they are equal. Since they are equal, the value should be equal to 1. Okay, up to Fermi level, say for example, this is Fermi level, up to Fermi level, okay, the value should be 1. Value should be 1. Right? And after Fermi level, right? After this, see, after this, all the levels, the probability is 0. Or Ni by Gi value is 0. We can say probability. This is also called probability. This is also called probability of occupying ith level. Okay, this is the graph you will get at 0 Kelvin. Right? Now, suppose if I increase the temperature, I'll increase the temperature to some temperature, say T Kelvin, or say T1 temperature. At T1 temperature, what will happen? Listen, at 0 Kelvin, you will get a graph like this. Now, what I'm going to do, I'm going to increase the temperature little above. Okay, above 0 Kelvin. Say for example, 20 Kelvin or 50 Kelvin, whatever it is. If you increase temperature, what will happen? Some of the electrons present in the Fermi level, they gain energy and goes to higher level. Okay, so what will happen? What will happen? Some of the electrons near to the Fermi level as well as near to the Fermi level will gain energy and goes to higher level. So what will happen? The probability value near Fermi level will decrease. So you will get Ni by Gi value 1 up to certain level. After that, the value will decrease, okay, and goes like this, right? And what happens here? Exactly at the Fermi level, the value should be off. Okay, so you will get this graph at some temperature, say T1 Kelvin. So keep on, if I keep on increase temperature, so if I go to another temperature T2, which is greater than T1, the T1 is greater than 0 Kelvin. T1 is greater than 0 Kelvin. Oh my God. T1 is greater than 0 Kelvin. Okay. If I increase temperature further, what will happen? Again, levels will be occupied like this. But whatever may be it is, see, at the Fermi level, whatever may be the temperature, at the Fermi level, Ni by Gi, our probability value should be half. Okay. So what is the other definition for Fermi level? Fermi level is the level where probability of occupying the ith level, that is Ni by Gi, should be equal to half. Fermi level is the level where Ni by Ga should be equal to half at temperature above 0 Kelvin. Above 0 Kelvin. Okay, so keep all these things in mind. These are all very, very, very important informations. Right? Sir, any doubt up to this? Anyone?
No, sir.
Okay, without derivation, I'm giving you the basic informations here. Okay, now, so this is regarding Fermi Dirac statistics. Okay, now we go to the next one. That is Bose-Einstein statistics. Okay. So the next one is Bose-Einstein statistics. Bose-Einstein statistics. What is this statistics says? Okay, what are the important points? Here also the particles must be identical. Particles must be independent. Independent means there should not be any attraction or repulsion exists between particles. No repulsion, no attraction. That's what I'm saying. And the particles must be indistinguishable. Indistinguishable. Right? So these are the characteristics of particles. Particles must be identical, must be independent, and must be indistinguishable. Then second point. Here the particles have spin. The spin values of the particle should be integer. The particle should have integer spin. If particles have integer spin, we call those particles as bosons. Okay, we call those particles as bosons, right? Then, since particles have spin, they must obey Pauli principle. Pauli principle. But here we have bosons. For bosons, what Pauli principle says is that the total wave function must be symmetric. Must be symmetric with respect to exchange of two particles. Okay. Then next point. Here there is no restriction. There is no restriction on the number of particles. There is no restriction on the number of particles in each level, in each state. You can place any number of particles in a state. Suppose if you have 3 states, see, you can place any number of particles in state 1 itself. And you can place any number of particles in state 2, any number of particles in state 3. So there is no restriction. See, in the Fermi-Dirac statistics, okay, I told you in each state you can place only one particle. Whereas in Bose-Einstein statistics, there is no restriction. You can place any number of particles in, okay, in a state, right? Then, yeah. So these are all the informations we should keep in mind. Now, consider a system containing n bosons, n identical bosons. Let the total volume is constant and total energy also constant. Okay, I'm going to keep all these things as constant, right? And for Bose-Einstein statistics, what will be the thermodynamic probability formula? So what is the formula for thermodynamic probability? Okay. So now let me ask this question. So suppose I have 3 states, okay, and I have say 2 particles. In how many ways you can place 2 particles in 3 states?
3 ways.
Listen, this is not Fermi-Dirac strategy. You can place both the particle in the same state. This is one way, because there is no restriction, I told you, no? This is a second way. This is third way. Then you can place like this also. Then you can place like this. Then you can also place like this. All are allowed. All are allowed. So how many ways you can place? You can place in 6 ways.
6 ways.
Sir, this is the difference between Fermi-Dirac statistics and Bose-Einstein statistics. In Fermi-Dirac statistics, you can place only one particle in one state. Whereas in Bose-Einstein statistics, you can place any number of particles. Okay, no restriction. Any number of particles in a state. So 6 ways you can arrange. Okay, for this, you can also get this value using this formula. W is equal to, okay, thermodynamic probability formula. W is equal to Ni plus Gi minus 1 factorial, okay, divided by ni factorial into gi minus 1 factorial. These are all mathematical formulas available, so I'm taking the formula as such. Now listen, let me check whether this formula obeys or not, gives the correct answer or not. So how many particles are there? There are 2 particles. So 2 plus how many states are there? There are 3 states. 3 minus 1 factorial divided by 2 factorial into 3 minus 1 is also 2 factorial. So in the numerator we have 5 minus 1, 4. 4 factorial by 2 factorial into 2 factorial. What is 4 factorial? 4 into 3 into 2 into 1. And 2 factorial is 2 into 1. Another 2 factorial 2 into 1. So 2 2s are 4. 2 cancels. So 3 into 2, 6. I'm getting the same answer, see. Okay. So you can use this formula to calculate thermodynamic, to calculate number of ways of arranging particles, okay, in a given number of states.
Yes.
Okay, so note down this formula now. Let me take so suppose if we have energy level, a system has many energy level. This is ground level, this is E1, this is E2. Like this we have so many levels. Then let us take an ith level EI. Okay, like this we have many levels. In E0 level, in ground level, let us assume there are G0 states, and also assume that there are N0 particles present in E0 level, the ground level. Similarly, we have G1 states, okay, in the first exit level, which has N1 particle. Similarly, G2 states and N2 particles. Like this, we have here we have Gi states and Ni particles. Right, like this we have different arrangements. Now, in each level, okay, we have many ways of arranging the particle. This you can calculate using the formula. So, what is the thermodynamic probability for the ground level? Okay, which is nothing but N0 plus G0 minus 1 factorial divided by N0 factorial into G0 minus 1 factorial. Okay, using this formula, you can calculate thermodynamic probability for the ground level. Similarly, we can calculate thermodynamic probability for the first exit level, second exit level, and like this we can also calculate for ith level. Now, so what is the total thermodynamic probability? Total thermodynamic probability is nothing but, okay, product of all these things, right? That is W0, W1, W2, you have to multiply everything, right? Or by simply see multiplication, no, so we can represent multiplication simply as pi of ni plus gi minus 1 factorial divided by ni factorial into gi minus 1 factorial, right? This is the thermodynamic probability formula for Bose Einstein statistics. Take down thermodynamic probability formula for Bose Einstein statistics. Okay, then what is the next step? We have to calculate the most probable macro state. For this, you have to maximize the function. Okay, so we have the formula total thermodynamic probability equal to pi into ni plus gi minus 1 factorial divided by ni factorial into gi minus 1 factorial. This is a general formula. How to maximize this? How to maximize this? We have to maximize this. How to do that? First take logarithm, then differentiate this logarithm omega with respect to number of particles, then put this value equal to 0. These are the steps we should do. I'm not going to do, I'm going to give you the idea. Okay. But here, as I told you before, n and e should be constant. So by keeping these two constant, we have to maximize. For this, we have to adopt the Lagrange's undetermined multiplier method. And if you use that, you will get the final expression as Ni by Gi as 1 over 1 minus e power alpha plus beta into Ei. See the formula. The formula looks exactly similar like Fermi-Dirac statistics, isn't it? Hello?
Yes, sir.
Yes, sir.
See, what is the difference between Fermi-Dirac and Bose-Einstein based on this formula? What
Minus.
difference you can see? Yeah,
That's
yeah.
Minus and plus.
Yes, that's here we have minus sign. Right, sir. Here we have minus sign. So this is the expression for Bose-Einstein statistics. Using this formula, you can calculate number of particles. What this formula gives you? This formula gives that the number of particles in the ith level for the most probable macro state. Okay, so you can find number of particles in the ith level for the most probable macro state using this formula, right? So this is what we call as Bose-Einstein statistics, and you know very well Bose-Einstein statistics have a lot of applications. Okay, yes.
Sir, அது e power alpha plus beta I minus 1 தானே சார் வரும் கீழே
E power alpha
plus beta I minus 1 இல்ல ரெண்டும் சார்
இல்ல no sir, no, that's all. Here you have minus sign, that's all. See, in different book the expression may be a little different, but if you analyze carefully you will get same thing. Okay, in different book different expressions will be given, right? But all are one and the same, but you have to analyze the formula carefully. Why I am giving this is general notation which is given in standard books like Rajaram Kuryako's book, right? And you can apply this formula for photon gas. Okay, you know very well photons are bosons. So for photon gas, you can use Bose-Einstein statistics and Bose-Einstein condensate, Bose-Einstein condensation, right? Many applications are there, right? These applications, you know very well, Max Planck derived this equation. Okay, that is the radiation density. Radiation density is equal to 8 by h nu q by c q into 1 by e power h nu by kBt minus 1. He derived this formula, Max Planck derived this formula for black body radiation spectrum by assuming the photons as distinguishable particles. Sir, observe carefully. See the information. Max Planck derived this formula by assuming photons as distinguishable particle, classical particle, and he derived this expression. Okay, but now what we are saying, photons are not distinguishable particle. Photons are indistinguishable particle, and photons are bosons. They obey Bose-Einstein statistics. So using Bose-Einstein statistics, if you derive, right, listen, unfortunately, we get the same expression given by Max Planck. That is why this photon gas model is very, very important. We discuss under Bose-Einstein statistics. Okay. See, according to Bose model, photon is a boson. It's an indistinguishable particle. But according to Max Planck, okay, he derived the expression by assuming photon as a distinguishable particle, classical particle. Yeah. But both the expressions are one and the same. The reason is, say inside the black body cavity, Okay, if you have one photon, right, the number of photons produced and number of photons absorbed, you know very well, the atoms present in the present in the inner cavity will keep on release photons, and other atoms keep on absorbing the photons. Okay, so that the number of photons remains. There is a balance. There is an equilibrium between number of photons released and number of photons absorbed. Okay, so based on that equilibrium, okay, it was found that the result of the Bose-Einstein statistics is exactly same as the result given by Max Planck method. Excuse me, sir, are you getting the information?
Yes,
Hello?
sir.
Yeah, very simple. Max Planck assumed photons as distinguishable particle. Whereas now we know photons have spin. They are bosons. So if I treat photon particle as boson, okay, do I get a different equation? Okay, if I see, I'm getting the same expression given by Max Planck. Okay, why? Because see, the treatments are different. We should get different expression, but we are getting same expression because there is an equilibrium. Okay, there is a balance, right, between the number of photons produced and the number of photons absorbed in the cavity. Okay, because of that balance, right, the expression for radiation density is exactly same, okay, as given by Max Planck, right? Sir, any doubt? Anyone? Hello?